Syncing, 1, 2, 3. All right. Hey, folks. It's a long time no see. My goodness. Don't worry, I make videos to keep you company in my absence. All right. It felt a little like COVID to me, being stuck inside for a little bit, I gotta admit. You know, that's, you all, it looks like most of you survived the winter storm. Most of you. Pouring out for those who didn't. Okay. All right. Well, welcome back. It's good to have you. So as you saw, I held recording sessions that were completely optional of basically 2 lectures, which were continuing to code dynamical systems. And we basically shuffled up the schedule a little bit in the way I think I like, in that the first 3 weeks are basically us learning how to simulate and model dynamical systems and animate them, okay? So as such, I changed up the first homework to cover exclusively those things, okay? This is the first homework up right here, okay? So it is now currently up on Canvas. You can find it on the Files page. I'm gonna put it up in an Assignments tab so that way you can submit, all right? And this homework I'm gonna have due at the very end of next week, Friday at 5 p.m., okay? All right? Now, let me walk you through a little bit of what we're going to be doing. So this is going to set the tone for how we're going to complete homework assignments in the future, okay? Whenever you go on Canvas to submit your assignment, you're going to submit 3 files, okay? One is a PDF. And that PDF, I try to explain it in gory detail, just exactly what I'm looking for, okay? You know, I just need your name, the date, the course name, and just all of the report deliverables just all in a row. So if it says, you know, problem 1, include a plot, you put it in a plot. Problem 2, you put it in a plot, you put it in a plot. That way, the grader can just go and scroll through and say, oh yeah, those plots look right. Wonderful, all right? That's the first thing, and that's not a Word doc, that is a, what friends? PDF. We all know how to make a PDF using Word? All right, okay. Do a PDF. Generally good practice to send people PDFs if it's not something they're going to edit. Okay? Second is going to be basically a folder with your code. Okay? Basically, you're going to make a zip file. Okay? And for those who've never made a zip file, you can literally just Google it and say how to zip a file. All right? And that basically will take a folder and turn it into just one file you can submit. All right? And it contains your code. Okay? We want to be able to run your code and get the result that you got. Okay? And also seeing the code tells us like, something went wrong here. And typically we go through like, okay, minus sign. I'd say about 75% of all coding issues you'll run into are probably negative signs in the wrong place, just forewarning. Okay? But this allows us to take a look at your code, all right, and run it ourselves. A few other things we talk about here. One is, so I'll get to saving movies in a second here, because you'll be making movies, just like we did in the lecture. And you'll be submitting them, and it'll be really cool. All right? But there is a requirement that you comment your code for readability. And I try to explain exactly what I'm looking for. That means that all of your functions have a header, which is like your name, you know, just like I do when I'm coding in front of you. Your name, the date, what does the function do, and if it's a function as opposed to a script, what are the inputs and outputs? Okay? Just good practice for practicing coding, all right? We'll get to movies in a second. Because the last thing you want to be able to, that you're going to include is a movies.zip file. All right? Okay? That doesn't mean however you downloaded the latest, I don't know, Squid Game season, I don't know, whatever. But, I don't know, I try to be topical in this class. All right? All right? But you'll be asked to make some movies MP4 format. Okay? And what you learned in class basically gets you like 95% of the way there. And all I need to do is give you about 6 lines of code, and you can turn it into an actual movie file, MP4, that comes out of your animations that we've done in class. That's what you'll be doing for at least one part of this assignment. So you'll take all your movies, zip them up in a folder. I don't want it taking more than 30 megabytes of space. It should not take anywhere near that. Okay? I say that because it's actually very easy to accidentally make a 1 gigabyte video out of your MATLAB animations. It's very easy to accidentally do. Okay? I'll include some instructions on a supplementary document for how to do that. okay? But with everything you've learned in the class so far, you should be able to do these two problems, all right? Last thing I just want to say, this whole save movie thing, see that right there? So I want to make, I'm going to ask that you make a little variable at the top that's save movie, and if it's false, it doesn't save the movie. If it's true, it does, okay? That way when my TA is running your code to check it, he's not saving a bunch of movies on his hard drive. Okay, that's just the last little thing. So, any questions on the overall instruction set? Even though we haven't talked about the problems yet. Okay. You should be using the tools exactly as we covered in our coding lectures. Okay? So there are two problems. I actually made two new problems for you guys, for you folks this year. I was so excited. You have a question?
Yeah.
Yeah.
Do you like having separate folders for functions, or having one file and under the main code all your functions, or does it matter?
Whichever works for you, as long as it's readable.
Okay.
One thing, this is great. I'm glad you brought this up. What's your name again?
Logan?
Logan. Thank you, Logan. Yeah. It says each script, whether it's like problem1.m or whatever it's called, should run in MATLAB if the unzipped folder is the current active directory. So what that means is if you have a bunch of helper functions that you put in different files, they better either be in that folder, or if they're in a subfolder, you have to add them to the path. We have not done much adding to the path. We've just put a bunch of files in one folder for now. Okay. So whichever way you do it, just make sure that we can run the script and it runs the code. Any other questions? It's exciting. I recommend getting started on it though. So, which problems are we talking about? Okay, I made some new ones for you this year. I was so excited because I also do notice that there is a slight anti-correlation between how excited I am to make the assignment and how much the students enjoy doing the assignment. So I tried to mediate that a bit. Okay, all right, didn't notice that. But I had fun regardless. I talked about how optimal control can be used to model and control cancer therapy. Okay, this is a chemotherapy problem. I found the equations of motion for a common tumor growth model. I even cited it. You can go find the original paper and how I put it together. Okay, and you're going to simulate tumor growth with and without chemotherapy. There will be one showing tumor growth without chemotherapy for like 80 days and shows the tumor growth in volume, and another where you turn on the chemo, the cancer is detected 40 days in, you start chemo immediately, you see what happens to the tumor size. Okay? I'll give you the equations. You're going to use all your very practiced knowledge of how to do state space, come up with the states, simulate the system. I tell you exactly what I want in terms of a plot. There's no movie in that one, not applicable. Okay? And here's an even more funner one. Okay? Pendulum on a cart. Okay, this is a classic. I resurrected this one, but I added a twist to it. So here, this is a pendulum on a cart. Basically, it's a cart that slides around, and there's a pendulum that flops around on it. Classic nonlinear control problem. Okay? I'm going to give you the equations of motion right here. Okay? And you're going to simulate it. But I'm also going to give you a few different types of controllers to put in it. One is a passive simulation, which is no controller. Okay? That's no controller at all. It just swings around, you see it swinging. Okay? A feedback controller, which actually actively balances the pendulum when it's already up. A feed-forward controller. Hey, what's the difference between feedback and feed-forward, folks? Anyone remember?
Feedback has like a loop.
Yeah.
Right?
Yeah, so do you use any additional information with a feedback controller? Like such as, yeah.
Sensor.
Sensor information, right? So you can see when you look at this feedback controller, I can't withdraw on this screen here, but this feedback controller is dependent upon the position and angle of the cart. So it's like you're measuring those things, and I give you the controller, okay? You don't have to come up with the controller yet. That's later in the class. I give it to you. All right? This one's cool. It's going to make the pendulum kind of step to the side and still balance. So it's pretty cool. Now the feed-forward one, you might say, hey, we have a cool feedback controller. Why would you need a feed-forward controller, which is dumber? It doesn't need sensors. Well, the feed-forward controller, you can get it to do all kinds of wacky maneuvers. So I came up with this feed-forward controller. You'll say, look how random that is. Dr. Hibicki's lost his mind. He gives these points to simulate it. What does it do? Well, I'm glad you asked. How do I go back? Sorry. Okay, whatever. I had this brought up so you can see it. It's very exciting. I promise. No, it won't be exciting. We'll see. Here you go. Here you go. This is what it does. So this is my pendulum on a card here, right? All right. So you should make a pendulum do that. Okay. I gave you the controller though. All you gotta do is simulate it and animate it. Okay? I want you to animate all of the 4 parts I want you to animate. Okay? Doesn't need to look as cool as this, hopefully, but it doesn't need to. Okay? You can see I used the MATLAB fill commands that we covered in the lecture and stuff like that, and I rotated this cool looking stick-like pendulum. That's all cool. You don't have to do that, but if you do something like that, or cooler, I will be very impressed. And isn't that what matters most? That's right. Okay? And those are the 2 problems. Okay? So, any questions about the homework? Yes?
When does it due?
Friday, 5 p.m. next week. I recommend getting cracking on it. Okay? And please be mindful of the format of the submission. I was very specific. It'll become even more important in future assignments. So now it's a good time to get it right. Okay? Yes, question?
Is the PDF for both problems, or is there a PDF for each problem?
One problem that contains everything. There's a one PDF that contains everything. One zip folder that contains everything. So you'll be submitting 3 things, to use the technical term. Okay. Any other questions? All right. So, do a little hard reset. So far in the class, we lovingly call applied optimal control. At least I lovingly call it applied optimal control. So far, we've been doing some of this control part. We've been introducing you to the idea of feedback control or feed-forward control. How you simulate a system so you can do control on it, right? And you're going to be such experts by the end of next week with those 2 problems, okay? But we have not talked yet about the optimal part. We just touched on it a little bit at the very beginning of the class, but not much at all, okay? So we're going to give you an introduction to optimization. Okay? Okay. Now, someone, in their own words, what is optimization? Anyone want to hazard a guess? Or your own definition? Yes?
Trying to make something more efficient?
So I say make something more efficient. That's a good definition, yeah.
The best way to reach a goal.
The best way to reach a goal. That's great. I think these are all on the same exact path that I'm on when I think about what optimization is. So Dr. Hibicki's optimization definition. Optimization is the process of finding the best possible solution to a problem as defined by a numeric cost function. Okay? There's got to be some kind of number in it, right? We can all argue about what our favorite movie is. What's your favorite movie?
Monty Python and the Holy Grail.
That's a good one, Monty Python and the Holy Grail. Okay. What's your favorite movie?
Moulin Rouge.
Moulin Rouge. Another good movie. I haven't seen it since, what, not 2000? I won't, okay, but I remember good things. Now, you cannot optimize which movie is the best unless you can define numerically which one is better. I'm sure IMDb would love to try, okay? But on its face, you know, is Monty Python better than Moulin Rouge? If you ever wanted to know, there needs to be some number attached to it, some cost function, okay? All right, some numeric cost function. Okay, and an optimization is the process of finding it, okay? So what's a way that we could find the optimal movie? I don't know. It depends on your cost function. Maybe the cost function is take 100 random people who know the language of the movie, have them watch it, and then they give it a star rating, and you average it, right? Okay. Then you can search across the space of all possible movies, see which one fared the best. That would be your optimal movie. Okay? So we had to somehow assign a number in order for this to make sense. Okay? So optimizations, optimization problems can be defined by 3 key components. Okay? First one, as I talked about, is, oh, sorry, I'll go back. It's called a decision vector. Okay? Which contains decision variables. Okay? So we'll call the decision vector, we'll call it W. Okay? In a lot of textbooks, you'll see it called X, and that's totally appropriate. Except for the fact in applied optimal control, X is often the state vector. So we have to play this sort of musical chairs of notation. So whenever possible, I will try to call the decision vector W. All right? But if an X pops in there, just shout my name politely, and I will correct it out of force of habit. So that's your decision vector W. Because it's a vector, we can think of it as like a one-column matrix, right? Containing different decisions. W1, W2, all the way down to Wn. Those are all of our decisions. Okay? And they can be represented by, frankly, a lot of different things. They could be represented by real numbers, and that's what we'll do in this class. They could also be integers. They could theoretically just be categories of things, which you would just turn into different integers. Okay? And the way that you would notate this, and this is a general sort of notation thing, not even an optimization thing, is you would say that W is an element of all real numbers to the n. And what that means is that there are n real numbers that define W in a vector. Okay? To be clear, there's no reason you can't have complex numbers, integers, natural numbers. Do people know what those things are? You know what those things are, but you know, natural numbers. You could have it be the space of all complex numbers to the n. You make it the space of all, all these things, right? You can make it those. But in our class, we will mostly cover real numbers. Okay? And that makes sense for the context of control. If you have a chemotherapy optimization problem, you don't necessarily have to choose an integer number of cc's of chemotherapeutic agent to give someone. I can give them 3.16 cc's of a drug. It's totally a thing that I can do. A real number. Doesn't need to be an integer. Whereas integers can be super handy. We have some people in our lab doing some work with optimization with integers. And it's for things like deciding, am I going to decide to go left or right? And that's a binary decision. So we turn it into an integer of 0 or 1. Okay. Or you could decide, do I want my foot to be on the ground or in the air if I'm a walking robot? Okay? That would be an integer decision. Okay? So decision vectors. That's one. Number two is a cost function. Okay? And a cost function f is some function of your decision variables. Okay? If I know my decision variables, there should be a way to figure out my cost. Okay? So a scalar valued function meaning that it sends you back one number. One number. Okay? A vector can go in, something can go in, but a scale or a single number better come out. Okay? Cost is a scalar valued function. Lower cost Gesundheit. By definition means a better solution. Okay? So, if our cost function was about movies, and we wanted to judge movies based upon their star rating, generally high star rating is good, right? But if we want to make it our cost function where we want to come up with the maximum star rating, maybe our cost function would be negative star rating. Right? So the more stars we get, the lower it gets, and therefore the lower the cost. Okay? So this goes by a lot of other names. You might have heard of something called a loss function, an objective function, where less is more. Just like a cost, you want to minimize your loss, you want to minimize your cost, you want to actually minimize this thing called an objective function, even though intuitively it sounds like you want to achieve your objective and it'll be more. But in fact, an objective function, less is more. You might hear me accidentally say objective function instead of cost function. It's the same thing. Okay? I think at cost is just a little bit more intuitive. Okay? There's also things like reward function. And and utility function. Where more is more. Reward function is very hip phrasing in reinforcement learning, which is a subset of machine learning, which bears a lot of similarity to what we do. Specifically because we are trying to minimize a cost, they are trying to maximize a reward. Really, you can just put a negative sign in front, and all of a sudden they look very similar. Okay? Okay? So it's a scalar valued function. Any questions so far? Okay. All right. And finally, we've got constraints. Okay. See, these define considerations that must be obeyed. To solve the problem. Okay. With the cost function, your job is to just do as best as you can. Get that cost as low as possible. All right? If I'm in a race to get to the door, maybe my optimization is set up in a way where my cost function says, get to the door as fast as possible. Okay? So it'll come up with decisions that I make along the way to get there as quickly as I can. Or I could make it a constraint that I gotta get to that door in under 1 second. That's not gonna be possible, right? It's completely, you can add a constraint that makes your problem impossible, right? Or you could use the constraint as another way of saying, get to the door in a short amount of time. You'll get to that door in 10 seconds. I can get to that door in 10 seconds, I'm pretty sure, right? And then something else could be my cost function. My cost function could be minimize the amount of effort to get to that door in that time. Okay, I got 10 seconds to get out of that door, all right? Someone gonna time me? Okay, you know what to use with flow. Someone count down from 10. You have your phone out. Okay, you're right. You're right.
You have
Ready?
to time
Yeah, but you gotta calm me down. Yeah. Let me go 10, 9. What do you see? 10, 9, 8 on the thing.
Okay.
Okay. All right. Ready?
Yeah.
Go.
10, 9, 8.
Optimizing.
7,
Optimizing.
6, 5, 4, 3, 2, 1.
Oh, thank you. Deserves a round of applause. Thank you. All right. Yeah, you can tell that. It made sure that. Thank you very much. What's your name again?
Alan.
Alan. Thank you, Alan. It's been a while since I've seen you all in person. It's like a whole new year. And so I added a constraint that made sure I got to the door, but my cost function could do something else, right? Because if I were what would it be like if my cost function was me trying to get to the door, was minimizing the time to get to the door? I'd be sprinting, right? I might trip and hurt myself. Okay? So you can see there's an art to how you decide what is a cost function and what is a constraint, right? Okay? Especially when you care about multiple things. I care about getting out the door, but I also care about not getting tired, or I care about not hurting myself. Okay? That's constraints in concept, right? In practice, there are two types of constraints. There are equality constraints. The way we write those is that they are G sub EQ of W must be equal to 0. And inequality constraints, call it G in EQ of W is less than or equal to 0. Okay? So I could formulate that constraint of me getting to the door as an equality constraint, where I say I must get to the door at exactly 10 seconds. No more, no less. Or it could be less than or equal to 10 seconds. Okay, just as long as I get there in 10 seconds, right? And you can fit any kind of constraint in these two forms. Any kind. If it's time to get to the door must be equal to 10, how do you make it equal to 0? Well, subtract 10 from both sides. Done. Now it's equal to 0. Surprise. Okay? And when you use a lot of optimization packages to solve optimization problems, many of them will ask for your constraints in this form. Oh, what's your GEQ? What's your G in EQ? One must equal 0, one must be less than or equal to 0. And unlike a cost function, which gives you how many numbers back one number. You can have as many constraints as you want. Okay? So these don't have to be scalar value functions. These are vector valued functions. Okay? Means that you can define as many constraints as you want. And if they're equality constraints, every single one of them has to be a 0. If they're inequality constraints, every single one of them must be less than or equal to 0. Okay? And that's it. Those three things define an optimization problem. And believe it or not, if you know that, you are well on your way. You can probably actually apply a lot of optimizations right now. You can grab MATLAB and open it up. It'll ask you, how many decision variables do you have? How many costs? What's your cost function? What are your constraint functions? Oh, it'll try to solve it. Okay? So a lot more of optimization is about setting up the problem than it is even about solving it a lot of the time. Because many, many people have written solvers to how to solve optimization problems. Now, they are not magic. They come with strengths and weaknesses. And in fact, it can really matter how you choose to set up this problem, because the optimization may work or may not work. Okay? So, setting up the problem is a majorly important task. Okay. You can also write code to solve the problem, and we'll do some of that. And MATLAB also has built-in solvers. Okay. All right. So, setting up the problem is a majorly important task. And in fact, if you set it up in certain ways, it becomes way easier than in other ways. Okay? We'll get that in a moment, though. Okay? Let's talk local. I'm sorry, I'm going to back up. I'm going to change the thing. We're doing an example. Can't go on without an example, right? I'm sorry, friends. Okay? And we've seen this one before, but let's go through it real quick. Call it the fencing problem. Okay? And you want to maximize the area of a rectangular fence. So you have this, you got a fence. Here is the width, and here's the height of the fence. Okay? Where you only have 40 meters of fencing. Okay. Let's set up our decision variables, our decision vector, our cost function, and 3, our constraints. Okay? What decisions do we have to make? What are our variables that we get to choose and change to come up with a better solution? Height and width, exactly. So our decision vector has our height and that's a capital W. I'll put a little hands and feet on it so it's super clear. Lowercase w on the left, capital W on the right. I'll do it over here as well. Yeah, Greco-Roman W right there. Okay. All right. That's your decision vector. These are your decision variables. Okay? Sorry, decision vectors, decision variables. All right. Now for our cost. Okay? Our cost, some function of our decision variables, f and w. We want to maximize our area. So you might say, hey, shouldn't our cost be our area? Nay, I say, because that would minimize our area, right? So one way to maximize it, real easy way, negative. You could do reciprocal, that's another way to go. I recommend the negative. I recommend it. Far less likely you're going to end up dividing by 0 at some point by mistake. That can easily happen. There are other mathematical reasons too, but that's the easiest one to think of. Okay. All right. So that maximizes area, right? Now for our constraints. Okay? We have our constraints. GEQ of W must be equal to 0. And G in EQ of W must be less than or equal to 0. Any thoughts on the constraints? How would you write them? Or you need to tell me in words. What are the constraints we have? Yeah.
Perimeter equals 40.
Perimeter equals 40. Okay? Right? So you can write that, sounds like, as an equality constraint, right? So you could say that, hey, I have a constraint that my perimeter, 2W plus 2H, must equal 40. Right? Now, is that GEQ? Not quite. Because it has to equal not 40, but 0. So that's not GEQ, but 2W plus 2H minus 40. That does equal to 0, but that is not equal to 0. Therefore, this is GEQ. Sorry, I didn't write that right. It's GEQ. So W is GEQ of W. So that's your GEQ. Do we have any inequality constraints? I don't think of any. Yeah, what are you thinking?
Would we be able to say like that the height and width have to be positive values?
That's. Can I give you credit in like 60 seconds?
Yeah.
All right. I like what you're thinking. You're thinking about whether they have to be positive. Well, you know what? Actually, let's do that right now. Okay. I didn't even think of that. I'm thinking of the next step, but it's actually true. Because by default, in this class, W is an element of all real numbers. The real numbers are negative, right? The optimizations, they can be really clever. If you don't tell it it can't be negative and it thinks that there is an advantage to it, it'll do it. I'll come with a quick example. I was doing an optimization project where I had a robot. I apologize if I told the story this term. It's starting to blend together now. Where I had a robot in a simulation. I wanted to get from there to there, all the way across the room in as little time as possible. And it was deciding how much time it would spend on each foot, and it was going to run, and it would spend how much time is it going to spend in the air versus on the ground. All those decisions were variables, right? So what it did was I ran the optimization, and I was supposed to go there, and it jumped backwards. What? And then right before it was going to land, it said, I'm in the air, but my time duration, for which I'm going to be in the air again, is a negative big number. So it reversed time in a parabolic trajectory and landed all the way over there. Because I didn't tell it that time can't go negative in its simulation. It'll do that. The optimizations are that clever. It, honestly, it's the first time when I was coding things up, I was like, that's magic. This thing is like magic smart. Really? And like it's, I feel like these days, the AI world gets all the credit for all these super smart computers, which effectively they're tuned with, they're trained with optimizations. They do a lot of cool stuff in their own right, to be clear. But like my first experience of having this thing just be smarter than I was was just running an optimization. And that was it. Okay? And it really gave me that sort of like, that genie conundrum, you know, careful what you wish for. Because you just might get it. Optimizations are the genie. They're the genie. So, anyway, that's just my experience with optimizations. Read into that what you will. Okay, so, you gotta be careful what you ask for. So if we have inequality constraints, and if you wanted to say that height must be greater than or equal to 0, and width must be greater than or equal to 0, that's not less than or equal to 0. How do we make that less than or equal to 0?
Negative.
Multiply both sides by a negative. So you multiply by negative, multiply by a negative, and that flips the inequality, right? So now they're both less than or equal to 0. So that means this here, that's G in EQ. Okay? Of W. So G, that's a Q. So GEQ of W is equal to 2W plus 2H minus 40. G in EQ W is equal to a vector minus H minus W. We set up the optimization problem. Okay? What I was going to do before Jack gave me a reality check here was I was going to say, hey, there's other ways that you can formulate this problem as written in my problem. It says you only have 40 meters, right? You don't necessarily have to use 40 meters of fencing, right? So it could be that this must be, this could be an inequality constraint, right? So you can use less than or equal to 40 meters of fencing. Great idea. I love it. Okay? Well, then you run into a problem that Jack preemptively solved. Right? What if your width was minus 1,000 and your height was minus 1,000? Is that a good solution? It's a possible solution, but according to our cost function, is it a good solution? It's an amazing solution. It's 1,000,000 meters cubed, right? Positive. So if you didn't allow it to go if you allow it to go negative, it's possible you come up with an impossible solution that it thinks it's awesome. Right? Make sense? Okay. That little simple problem has a lot baked into it, okay? The little fencing problem, okay? All right. Now let's talk a little bit about local versus global optima. Optima is the plural form of optimum. Okay. Okay. All right. And we're trying to minimize things, so we'll talk about minima, right? So let's say you have one decision variable, W, single decision variable. Here's your cost function. Okay? I'm going to draw this cost function. Just like that. Okay? Anytime that a continuous curve, anytime that a curve hits a point that is lower than both of its neighboring points, it is locally a minimum, right? This is local. These are local minima. They are both local minima. Okay? But we can look at this, we know that one is actually better than both of them, right? Okay? This here That's lower than all of them, of the entire possible set of minima. This is the global minima. Okay? All right? Global minima are great if you can find them. If you can find them. All right? It is far easier to find local minima. Okay? So just off the top of your head, anyone just remembering calculus at all, what's a good way to find a local minima? Assume that you have a cost function, assume that that's written out as a function, and you have, yes, yeah, what do you think?
Slope is equal to 0.
Slope is equal to 0. Exactly, and the slope is, of course, with respect to w, right? So that's the derivative of f with respect to w, right? So let me just write this out. So local minima are easier to find. We'll say with continuous / differentiable functions. I'll remember continuous and differentiable, I would assume. Okay. That if you have partial f of w, partial w is just, you could just treat it as an ordinary derivative, but with one variable, but if we have multiple variables, we want to use partials. Is equal to 0, right? That's because there's a slope, it's equal to 0. Right? This has a fancier math name. Does anyone know the fancier math name of this? Yeah. Yeah, you. Did you raise your hand? What's that?
It's called the gradient.
The gradient. Oh, yeah. You know what? You're all right. This thing is called the gradient when w is a vector. You're totally right. And again, you're all ahead of me. It's okay. It's a good thing. All right? But this condition here, where the slope must be equal to 0, it's called a first order necessary condition. Okay? First order necessary. Why first order? Well, it's a first order derivative, right? Why necessary? Because this must be true in order for it to be a minimum. It's got to be 0. Okay, well, don't conditions must be true? You know, well, it's more complicated than that. Because are there conditions where this is satisfied, but it's not a minimum?
It's a maximum.
It's a maximum. Or it's a saddle point, you know, kind of a critical point, right? So there's also that. There's also that. So this must be true, but in and of itself is not sufficient to say it's a minimum. Okay? So instead, how would you know mathematically if that point is a minima or maxima or a critical point? Yeah.
Is the second derivative, like the sign of it, will tell you?
Yeah, the sign of the second derivative. Correct. The if it's concave up, right, it's going to be a minimum in that area. The second derivative will tell you that. So the second derivative, partial, f, with respect to w, must be greater than 0. This is called a second order sufficiency condition. So these two together, the necessary and the sufficiency conditions, tell you if you're on a minimum. Right? All of these satisfy the necessary condition. This must be true. Then you check the sufficiency. Oh, that's concave down. Oh, that's going to be a 0 saddle. Oh, that is positive. So that one is a minimum. Any questions about that? Okay. So, because we can write these conditions very cleanly for local minima, we actually have great ways of finding local minima. All right? But that does not mean there isn't a better local minima somewhere else, and therefore a global minima. Right? Okay. That said, in this class, we will almost exclusively be doing optimizations that find local minima. They're amazing. And a lot of the time, I'll say a lot, more often than you'd think, they are effective with the global minima for optimal control problems. Okay? All right. That's sort of a preview, because it's kind of the classic, you know, I'm new to optimization. That's just the local minima you found right there. Are you sure it's not the global minima? And I'm like, my answer is like, I don't care. I don't care if it's the global minima. It's good. I got it quickly, and it does the job, right? And often you look at a solution, you're like, oh my goodness, that is the global minima too. That happens a lot of the time. All right. So you have your first order necessary conditions, your second order sufficiency conditions, right? And I wrote them in this kind of familiar language. You've seen partial rooters. You all took Calc 3, okay? And that makes sense where W is a single variable. But as you mentioned, when you have multiple variables, there's something called the gradient, right? So in general, the first partial derivative with respect to a vector is called the gradient. Okay? Right? Okay? Now, I'm not so great at drawing surface plots on my iPad, so I won't. Now, I was almost going to try, but I'm going to stop myself. Okay? I'm going to do it. Do it. Here's X, Y. Oh, actually, here we go. We're going to do it. All right, we're going to have W1, W2. Those are two of our decision variables, right? This will be our cos function, W1, W2. Okay? All right. I'll do it in a different color for funsies. All right. Draw some ribs here. Not the worst in the world. Sort of like a 3D surface, right? Okay. And I'm going to draw right here. According to my 3D drawing, that's about the minimum. It's sort of it's like a scoop. Okay? All right? So that right there, that's the local minimum we'd be trying to find, right? Now, we could try to solve the partial derivative of f of W1, W2, and says the partial derivative equals 0, and we can solve it physically. We could try to solve it physically, yeah. With a pen and paper, solve for where it equals 0, what W1, W2 do that. You can do that, right? Okay? And we'll get to that in a second, right? But the cool thing about the gradient is, let's say instead of solving it, we try to iteratively guess what it is. Let's just guess that this point, W1, W2, is the best solution. It's not, we're guessing. Then we go and we check what the value of the cost function is. Okay? Then we look at the gradient. We check the gradient at that point, right? And that's the slope in multiple directions, right? That's what the gradient is. Gradient. And say it points in that direction. Well, let's make a new guess. What direction do you think our guess should move? In the direction of that arrow, right? So let's kind of project the shadow of that arrow down onto the plane right here to choose a new W1, W2. Right? Then we check the value of that. See what's the gradient now? That, you see where this is going, right? You are taking a point, you're guessing, find the gradient, and you descend the gradient until you find your solution iteratively. This is a method. Does anyone know what it's called? Gradient descent. You wonder how all manner of gradient descent is used all over the place, especially these days. All those AI models that people use or don't use for their homework are trained using gradient descent. There are different variants. There's stochastic gradient descent, but they work because of gradient descent. They are optimized. There are a bunch of W's, billions of W's, probably trillions of W's. I forget how many. It's billions at least of W's that they have to figure out what they need to be in order for ChatGPT to work. Or DeepSeek. DeepSeek is the new one. DeepSeek, right? And they use gradient descent to find the best. Okay? So, it's called the gradient. So this is a gradient descent algorithm. Now, I'm just using this to show you why the gradient's important before I throw more math at you. Stop down for questions. Yes?
For this, like, the gradient descent process, is it separate for both the variables for W1 and W2, or they both, like, combined, like, working together to try to find where the
you could treat them effectively separate, but we do it all in one mathematical step.
Okay.
Okay? If you figure out what the derivative in one direction is, you can step a little bit, and the other direction you can step on it. It's equivalent. It's equivalent in this case. There are other algorithms that are faster that you don't want to treat them as separate.
Okay.
Okay? They can be faster. Okay? All right. So, all right. So let's go back to the gradient. Okay? Okay? The gradient, that's the partial derivative of a scalar valued function. And this, you know what, I'm going to write x, because this is much more general than just w. Okay, x. Okay? Partial f, partial x, where f is scalar valued, and x is a vector. Okay? And what does it give you? It gives you partial f, partial x1, partial f, partial x2, partial f, partial xn, where x is a vector with n elements. Or in a, as you might be used to seeing it, x is equal to x1, x2, all the way up to xn. Okay? So this gives you that. So the partial derivative of a scalar with respect to a vector gets you this gradient. And each of these things are just individual partial derivatives. And partial derivatives, those are the easy ones, right? Ordinary derivatives, boo. Partial derivatives, yay. That's just my opinion. I just love treating everything like it's a constant. Okay? So if you can take a partial derivative, you can take a gradient. If you dodge a wrench, you can dodge a ball. Okay? All right? But you got to do it more times. Okay. All right. So that's the gradient. But what? That's second derivative, right? It's second derivative. That's interesting, right? You have the second derivative of a scalar valued function. And you take the second derivative, again, all partials, with respect to some vector x. That's interesting. Well, what pops out? Well, let me name it first. It's got a cool name. Called the Hessian. Okay? And what comes out is a matrix. Okay? It's a matrix where in the first row you've got partial, second partial, and then two partials with respect to x1. Second partial, partial x1, partial x2. All the way up to second partial, partial x1, partial xn. So you'll see it goes 2, 3, 4, 5, 6, 7, 8, up to n. And this first one here is partial x1, or partial x1 squared. Second row, you have partial f, partial x2, partial x1. You have partial squared f, partial x2, or partial x2 squared. All the way out to partial x2, partial xn. You repeat this pattern all the way until you get to, let me make this bigger, I'm sorry friends. One day I will learn not to bracket my matrices before I write them, okay? All right, one day I will learn. There's partial f, partial xn, partial x1, pardon the terrible partial there, partial squared f, partial xn, partial x2, and then out here you've got partial squared, partial xn, so that's going to be squared. All right? So it's a matrix. You'll notice that it has the same number of columns as rows, so we call that a square matrix. Square matrix. It's n by n. And again, you can get this by just taking partial derivatives. Just take a lot more of them. And it looks like a lot, and it kind of is. That's all right, but relax, relax. Relax. I can help you a little bit. Here you see partial x1, partial x2. And here you see partial x2, partial x1. Does the order of the partial derivatives matter? It does not. The order of the partial derivatives does not matter. Therefore, this will always equal that. This will always equal that. This will always equal that. We call that matrix symmetric. Okay? It's always symmetric. And for those who haven't had a linear algebra course ever or in a long time, that just means it's symmetric about the diagonal. This diagonal. Okay? So that means if you solve for just the upper diagonal, the upper triangle here, you can just reflect it onto the bottom, right? Okay? And that's your Hessian. Okay? And this is going to be the most, the deepest we'll go into linear algebra here. Okay? Because I know it's not a prerequisite. Okay? But we won't deal much with it. But keep in mind that for the second order of sufficiency, that second derivative has to be greater than or equal to 0, right? Greater than 0. What does that mean for a matrix? Well, you might be tempted to think that means, oh, that means all of the elements have to be greater than or equal to 0. Wrong, my friend. Wrong. Wrong. It actually means that the eigenvalues of that matrix must all be greater than 0. Okay? We won't talk much about eigenvalues in this class, but just so I'll write that down. If you're curious about them, you've never seen them before, I can send you, I can post a lecture that I taught last class, last semester, where I talk about eigenvalues. Okay? See a question? No? Okay. So if that means partial f of x, partial x squared is greater than 0, that means that all eigenvalues of the matrix have real numbers greater than 0. Okay. And because it's a symmetric matrix, if you know your linear algebra, the eigenvalues will always be real and not complex. You'll have no imaginary component. But not required for this class. That's the most I'll talk about eigenvalues for the vast majority of this class. Okay? But what does that mean? That means we have a way of knowing that if this plot, this bowl here, is concave up or concave down, if it is 3-dimensional, 4-dimensional, 16-dimensional, 1,000-dimensional, even I won't attempt to plot that. Right? Which is important because while we don't typically think in more than 3 dimensions in our physical space, we think in many dimensions in optimization. Why? Well, you see it right here, right? Here I have just 2 decisions. Maybe it's my length and width of my fencing problem, my width and height of my fencing problem, right? And how would I have to plot this? Well, 1, 2 dimensions on one axis, cost functions of the 3rd dimension, right? What if I had a much more complicated problem, or even not that much more complicated problem? Let's say, how you drive to work, or how you decide to get to work. How many decisions were involved to do that? Okay? Every decision adds a new dimension. Okay? So, for some of my walking robots, I showed a video of a purple one, like those walking on a treadmill in the very first lecture I gave. That had, anyone would guess how many decision variables were in that problem, optimization problem? 4. Slightly low.
64.
Still slightly low.
200.
Slightly low.
1,000?
Slightly low.
10,000?
Correct. 10,000-ish variables. Right. Slightly low. Slightly low. 10,000. Right? So, could not plot this. But using basically gradient descent and algorithms like it, we've found local minima for how to make that robot walk. Okay? In fact, one thing I will do, I sort of did right here, is I tried to scare you with how weird and wacky it'll be when you have many, many variables, because you have this crazy surface that you couldn't possibly plot. And moreover, how could you possibly search all the different spots on this grid, right? Let's say you had 10 little tick marks here that you wanted to check for 1 dimension. That's 10 functions you have to call. No biggie for a computer. What if you had a 2nd dimension? Now you got to choose every combination of them. So now you have 100. 3rd dimension, 1,000. It's 10 to the n, right? And eventually computers can't keep up. It scales exponentially in a way that computers can't keep up. It's called the curse of dimensionality, actually. Okay. So that's why we don't search over all the possibilities individually. We use things like gradient descent that'll beeline straight for the answer and are much faster. That's why it only takes a couple minutes to search a space that's 10,000 dimensions for these robots. But there are smart ways and less smart ways to set up the optimization problem. That's a huge theme of the class. I'll pause for questions. Okay. All right. So that's the Hessian. So you'll notice that if you have a scalar valued function, and you take a derivative with the vector, you get this row vector. Okay? And if you take a scalar value function and take two derivatives with respect to a vector, you get this square matrix. What's it called? Hessian. Hessian, yeah. You can say Hessian, but if you want to be cool, you say Hessian. Okay? All right? But this is what I'll kind of finish with this little bit of math today. What if you didn't have a vector value function? You had a scalar value function. You had a vector value function. Kind of like our constraints, right? Where they return a vector. Not just one number, but could be many in a vector. So what if you did a partial derivative, first partial derivative of g of x, where this is a vector value, and you take the derivative with respect to x, which is also a vector. Okay. Okay. Well, we can do that. If you can take one partial derivative, you can take this. But prepare yourself, okay? So, where g of x, I'm going to put this up, so we're going to say that g of x is going to have several functions in it, g1 of x. I'm just going to write it in a row, but I'm going to mean it in a column, so I'm going to transpose it. Just hold on a second. g2 of x, all the way up to gm of x, transposed. So transpose, just as a reminder, that means takes a row, turns it into columns. Okay. And of course, we're going to have x is going to be our same old, up to xn transpose, so it's a column. Right? So what is this? It's a matrix, friends. Oh, what did I just do? Try to bound in the matrix before I wrote it. There's got to be a matrix. In the first row is going to be partial g1 of x, partial x1. Partial g1 of x, partial x2. All the way out to partial g1 of x, partial xn, because there are n x's. The g1 stays the same across the whole row. Then in the next row, we'll say partial g2 in the second row. Partial x1 in the first column. Partial g2 of x, partial x2, because we're in the second column now. Partial g2, still in that second row. Partial xn, because we're in the nth column. We continue down. It's partial. We're in the final one of our g's, gm of x, partial x1, because we're in the first column. Partial gm of x, because we're still in the nth column, so nth row, so, and partial x2, because we're in the second column, all the way up to partial gm of x, partial xn. And now we have our matrix, and now I'll put little brackets around it, just like someone who learns. Okay? It's a matrix. M does not need to equal n. You could have different numbers of g versus x. That's okay. It just means your matrix won't be square. That's totally fine. This is super cool and important. And it's a cool matrix. It's got a cool name, even cooler name, called the Jacobian. Okay? The Jacobian. The derivative of a vector with respect to a vector is a Jacobian. All right? You get it by taking lots of little partial derivatives, and that's it. Okay? I know we're at the end of the lecture. I just want to reiterate that this is actually super important tools. Not even just for this particular subsection of the class. Knowing how to take a gradient, knowing how to take a Hessian, knowing how to take a Jacobian, Good to know, you can even do it by hand. Did you know that MATLAB has some commands that are helpful in this case? One's called gradient, one's called Hessian, and one's called Jacobian. They are also helpful. Okay, and with that, I wish you best of luck for your homework. We will meet remotely on Thursday. Okay? And I wish you luck. Talk to you soon.